Hello and welcome back to Let's Code Physics. I hope you've enjoyed watching Star Wars Episode 7 in your home. I'm sure that by now there's been plenty of discussion on the internet of things people missed in the movie theater, trying to figure out if there are any clues as to who was the actual Force user among the two new main characters, or how they tried to fool you about it. Speaking of being fooled, we are here to talk about the physics of lightsabers and whether they are feasible, and if they were feasible, what kind of power they would require. The way we're approaching this is that we're assuming that a lightsaber needs to be built out of something called a Fourier series. The way a Fourier series works is that you can take any function and represent it as a series or a summation of sines and cosine functions of different wavelengths. The way you would set it up would be you would have some base value plus a summation over cosines plus a summation over sines, and it's these coefficients, these ANs and BNs that you would need to specify in order to get the function that you wanted. Now there's a little bit of a caveat here in that this is an infinite summation, right? So you're adding up an infinite number of pieces. We can't really do that in real life. So for the computer, we're going to have to settle for infinity being something more like 50 or something like that, or 500. We can increase the number. But the function that we're looking at to integrate over is pretty straightforward. We're looking to create a lightsaber, so we want a wave. We want some kind of wave structure that is constant from 0 to the beam length and then 0 everywhere else. And the way we're going to get these is through some integrals. So we have to get these coefficients, the A0, the AN, and the BN. Those are obtained through these integrals. They're weighted by these factors here. And our function is just going to be 1 if x is less than the beam length, and it's going to be 0 if x is greater than the beam length. Really what the effect of that is, instead of integrating to L, we're going to integrate to the beam length. So I've already got most of this code set up here. I think I need to check a few things. For example, I need to make sure that I'm multiplying by the correct factor out here. So what I need to do is I need to give it an x-min and an x-max. So that's the space that I'm looking at. So if you like, x-min is 0 and x-max is however far I'm integrating to out here. So out here is going to be x-max. That's also our L in these integrals over here. And our x-min, that's going to start at 0. And so our beam length is going to be somewhere less than the x-max. So we're integrating out to 10. Our beam length is going to be 1. So if you like, this is a 1 meter lightsaber that we want to make sure has 9 meters of clearance. And I mentioned earlier, we can't really take n all the way out to infinity. We're going to settle for 50 for right now. We can increase that later and get an idea of the change that results. And then, of course, I also need to tell it, when I go to graph this function, I need to tell it how many x points to consider. So we're going to consider 500 x points. Basically, this just needs to be a larger number than n max is kind of the most important thing. So we look at our functions to integrate. We took a look at the general way to structure this last time. We need to define some external functions. So I've defined an A integral and a B integral. So again, this is just going back to here. The A is given in terms of the cosine. This thing is going to be 1 when we're actually integrating it. So we have a 1 times cosine 2n pi x over L, 2n pi x over L. Cool. And we've got the B integral is sine 2n pi x over L, sine 2n pi x over L. Again, this f is just going to be 1 or 0, so we're really going to integrate to the beam length. Okay, cool. So the A0, the first constant that we're looking at, is given by this integral here. And it's given by 2 divided by the length times the integral of this function. So this function is just 1 for 0 to the beam length. So that gives you a value of the beam length here. It's getting divided by x-max, and I did forget the 2, so I'm glad you are here to walk me through this to find my missing 2's. And then down here, we are calculating the AN and the BN integral. So you only need one A0, but then you need an A and a B for every N, for every term that you're looking at. So here we're doing integral from x-min to the beam length of ANT. And again, that's this function up here. We're dividing by L, so I need to multiply. I need to add in a times 2. Same thing down here. I need to add in a times 2. I converted a formula over from Wolfram Alpha and left off a few 2's. My bad. Cool. And so what we're looking at is getting these coefficients. That'll be pretty cool. These will come in later, so let's talk about these in just a minute. That's for the actual physical interpretation. First, we're going to see if we can create the shape of a lightsaber, and then we'll worry about the physical interpretation. So let's come back to that in a few minutes, I promise. Cool. So once we've gone through that loop, we have all the ANs and the BNs. And then to get the function back, to actually create this function out of these waves, we just have to set up this equation here. 1/2 A0 plus the sum of all the ANs times their cosines plus the sum of all the BNs times their sines. Cool. So let's see here. So we've got we're setting up our dx here. That's just our x step. It's the x range we're looking at divided by the number of x values. I'm keeping track of a counter here for some arrays. Let's see here. So we've set up our for loops. We're going to go from x min to x max. So we're going from 0 out to the L, the x max that we're looking at. So the beam length is somewhere in there. So when we graph this, what we should see is a pretty flat line that goes out to the beam length, which is 1 in this case, and then nothing for the rest of the screen. Cool. And so for each x value that we're looking at, we've got to evaluate the summation, right? So this summation, you've got to evaluate an infinite number of terms. So remember, 50 is infinite for today. So this is when you have your 50th birthday, say, oh, but Let's Code Physics told me this was my infinite birthday. The infinite birthday. That sounds like a good movie. Can't tell if that's a science fiction movie or a Nicholas Sparks movie. Maybe it's a science fiction Nicholas Sparks movie. Nicholas Sparks, hit me up. We can write a sci-fi romantic novel together. Let's see. Anyways, but this is being evaluated for every value of x that we're interested in. So we've got to do this within the x loop, and we need to then loop over the n values. And basically what I'm doing is I'm storing the x values in an array, and I'm storing the y values in an array so that we can graph them later on here. And then again, we'll worry about frequency and power a little bit later on. Frequency and power. That also sounds like a good sci-fi novel title. Okay. So let's see here. So if this works, what we should get is something like this where it's flat and then goes to 0. So let's run the code, see what we get. Okay, and we get a decent approximation to it, right? So the beam length is 1. So here is your lightsaber. This is looking more like Kylo Ren's lightsaber because it's all jaggedy. So I told you last time, Kylo Ren apparently doesn't know his Fourier series all that well. I hope he's not watching this video. Okay, I'm just kidding. Sorry. Let's see. So because I'm using 50 terms instead of an infinite number of terms, this is kind of wavy. And then because I'm using 50 instead of infinite, this is still a wavy instead of being perfectly 0. But you notice it is oscillating around 0. This one is oscillating around a base value of 1. If I wanted to change the length of the beam, let's say I want my lightsaber to be 2 meters long instead of 1 meter long. Now what I should get is I should get the flat part extending out to 2. Let's see if that's what happens. Did I get a new graph? Not sure whether I got a new graph. Oops. Error, round off detected. There are tested taunts. Oh, that's right. I ran into this issue. There was some issue with the integrator. All right. Let's try 1.5 instead. The problem with using an in-house integrator is that you don't really have a whole lot of control over it. Okay, so by changing to 1.25, basically I was giving it too much to integrate, and it was throwing an error for me because this was changed too frequently. But here I've got this extended out to 1.25. So, or let's say I wanted a light dagger instead of a lightsaber. Do they have light daggers? It would make sense for them to. Here, you get it out to a 0.2. The problem is you're only getting this peak, right? So it's not looking too much like a lightsaber there. So let's stick with a beam length of 1. There we go. But now, so there's a couple of problems with that. I mean, we're getting the basic shape, right? But there's a couple of problems. One is that it's all wiggly instead of being this nice, flat, lightsaber. And the other problem is that we're not quite getting 0 at the end there. There's actually another problem, and I've kind of hidden it from you. Watch what happens when I extend the area that I'm plotting it over, okay? So I'm still going to be integrating from 0 to 10, right? So my lightsaber is valid from 0 to 10, right? But let's see what happens when I graph it for more than that. Watch what happens here. you notice what happens is you get your lightsaber here from 0 to 1, but then you get another lightsaber here from 10 to 11, and another lightsaber here from 20 to 21. What's going on here? What's going on here is that the wave nature of the sine and cosine is coming to rear its ugly head. Because as long as I use a finite number of terms, these things are going to repeat itself. The whole series, the whole summation is going to eventually repeat itself to where the shape that I created here is going to get recreated here, and then it's going to get recreated here. The way I can fix that is by increasing my x max, increasing the distance by which, or excuse me, the distance over which I'm integrating. So let's increase this to 30. And now, instead of the beam going from, instead of the beam reappearing at 10, it's reappearing at 30. So I've extended it out a little bit. I've made it a little bit better, but the beam is still repeating itself. So really, what should really be happening every time they open up a lightsaber, they should get a beam here, and then some distance later, maybe some number of parsecs, Star Wars writers, because parsec is a unit of distance, not a unit of time. I know they explained it in the novels, but then you took the novels out of canon. Sorry, gripe over. There should be another lightsaber some distance away, and then another lightsaber some distance away there. So every time a Jedi swings their lightsaber in one place, there's this random beam of light that cuts around, another area some distance away. Now, another way you can fix that, we can make this a little bit better. Let's turn x max back to 10. So we're getting back to our previous shape there. And let's see, so we now know the problem of having an infinite number of lightsabers around the universe. Let's see what we can do to make this thing a little bit flatter. The way to address that is to use more ends, is to use more terms. Let's see how this improves when we change this to 100. And then let's change this to 1,000. Just so that way we continue to make our graph smooth. You notice it gets a lot flatter. It's a lot better looking. It's not quite there yet, but it's definitely better than it was before. Oh, and you know what? I think I need to remove this one. Do I need to remove that 1/2? Actually, yes, I do. Excuse me. I need to remove that, so that way it'll start at 1. No, it's still not starting at 1. Okay, never mind. Leave it on there. Excuse me. I'm just breaking Fourier series. Don't mind me. Let's see. Let's get this thing up even more. Let's get this thing up to 500 and 5,000 here. Now, of course, the problem is the more the more steps I include in the code, the more iterations of the loop that I have, the excuse me, the longer the code is going to take. So let's just make sure that this thing is running. Yes, I'm getting the spinning wheel of not quite dead yet. How many movies besides Star Wars can I reference while talking about Star Wars? I'm sorry for getting upset earlier. It's just, as a physicist, when a sci-fi movie, genuinely, encourages people to think about science fiction and think about things think about, different technological things that are possible. It's great. And then when they do something like refer to parsecs as a unit of time, it just kind of ruins it, which is actually, I think what we'll find out in this lightsaber thing is that, Star Wars is probably more correctly classified as fantasy rather than science fiction, because it's not trying to inspire you to build a lightsaber the way Star Trek inspires you to build a transporter. It just wants you to imagine that, lightsabers are out there somewhere. So what do you notice we get here? We had 500 terms. It took a couple minutes. So this took our lightsaber a couple minutes to actually get out of the casing. So this would not be a very effective lightsaber in battle. But you notice it's a lot flatter. So if you keep increasing those number of terms, you end up with this thing being a lot flatter, which is really great. Okay, so we've talked about, let's decrease this back to 50 for right now. So we've talked about sort of what the lightsaber would look like. Let's talk about the power requirements. Because when you think about it, for every one of those waves I add in, it's going to require more energy from the power source of the lightsaber, right? And so, roughly speaking, you could say that the absolute value of each of these A's and B's is sort of the power required for that wave. Now, there's probably a more formal way to actually get, physical power out of it. But the stronger, the higher the error the more power it's going to be. So think of this as power in quotation marks. Also, we got to think about the frequency of this, because energy of a photon goes up with the frequency of of light. For every photon you have, you need Planck's constant times the frequency, that much energy to produce it. So here we're calculating the frequency as the speed of light divided by the wavelength. Should that be half of x max? Yes, excuse me. Yeah. That's right. So this is going to be the speed of light times the wavelength, n divided by half of x max. Cool. So what we're going to do now, instead of worrying about plotting the lightsaber, we're going to plot the power spectrum. So what this is going to show us is how much power is required for each of the light frequencies that the lightsaber emits. And let's go back down to 50 just to make it nice and simple. Okay, cool. So, you see this thing bouncing down to 0, for example, because, it doesn't need every term. But you can see there's kind of this general trend going down here. The question we would ask then would be, what does that trend do? Because you're getting higher and higher in light frequency, right? So that's higher and higher on the spectrum, right? So this is the energy required, and this is the amount of power you've got to devote to putting out that much energy, that much frequency of light. And it seems to be going down, kind of exponentially or so, which would be an interesting scenario. Let's get a few more data points. Let's up this back to 500. Let's put that back to 500, so we've got plenty of data to work with. We are back to the spinning wheel of waiting for the code to finish. Okay, there it is. What you notice is it's decreasing and it's kind of leveling out. Here's what I'd like to do. I'd like to get this on I want to be able to see, the differences there. So here's what I'm going to do. I'm going to access the, where are you? Where is the variable browser? There it is. The variable browser is a really neat feature in Scilab. I think I already had it open. Here we are. Okay, so here's our variable. Here's our variable browser. So if I take a look at this PAL, this is the absolute value of each of the ANs and BNs. So here's what I'm going to do in order to be able to graph this a little bit better, because I've been having trouble getting Scilab to do a log plot ever since I upgraded to, ever since I added in a library of called Plotlib. It was for a student's project. He was using Plotlib. So now my computer is stuck with Plotlib on there, and I can't get it to do a logarithmic scale. Let's do frequency and power here in Excel. So let's see here. Let's open up frequency. All right, so we're going to copy. This is just so that we have something to plot on the x-axis. What I want to do is I want to look at what's the trend of the power. Can we extrapolate some kind of trend? Because we need an infinite number of terms to get a perfect lightsaber, right? So assuming that there's not that problem we talked about earlier of an infinite number of lightsabers slicing across the galaxy, let's see what happens if we were to extrapolate this thing out to an infinite number of terms. Does it ever truncate? Does it ever, get down to 0? It looks like it gets pretty close to 0. But again, let's see what happens when we turn this thing into a log scale. Let's see. That's a very good girl, Punkin. You are very strong, and you love the drama of the Let's Code Physics, don't you? Sorry, I have to praise my cat every time she scratches her post. So we've made this thing into a log scale, and what we notice is we've kind of got two different trends going on here. We've got these, so these are basically the zeros, right? These are basically the frequencies that you don't need any of, right? So these are the ones all the way down at 10 to the minus 17. That's a computer's way of saying 0. So really, let's even zoom in a little bit here. Let's make the minimum, it was 1e negative 4. Okay, cool. Yeah, so we got a few different trends going on here. There's probably some actual mathematical analysis I could do with that. But what you notice is that they're kind of leveling off. They're not really showing any signs of, heading towards 0, which would be, infinitely low on the y-axis. But this thing is getting flatter and flatter as it goes along. What that means is that if I keep iterating this out, if I go out to 1,000, it's still going to get flatter. If I go out to 1,000,000, it's going to get flatter. If I go out to 1,000,000,000, it's going to get flatter. What that means is, remember, you need an infinite number of terms, and each of these terms requires something non-zero. So if you take a bunch of things that are not zero and they're approaching a flat value, and you add up an infinite number of them, you're going to end up with an infinite result. So in other words, this little code here and this little graph here indicates that in order for a lightsaber to actually work, you need an infinite power source in the lightsaber. So based on that analysis, if the assumptions we've made are correct, if indeed, Fourier series is the way to build a lightsaber, then a lightsaber does require an infinite amount of power. So sorry to burst your bubble, but I don't think we'll be building a lightsaber anytime soon. But hey, maybe now we can be a little bit easier on Kylo Ren for having such a funny looking lightsaber in the movie. Anyway, thank you so much for watching. This has been a really fun project, and it helps address this question: can we actually build a lightsaber? Fourier says no. So maybe the Star Wars writers will not be listening to my request to name a Jedi after Fourier anytime soon. So thank you so much for watching. I will see you next time. Bye-bye.